how that happened. Anyway, so I have about 10 minutes. I'm going to explain all of Plasma. No, I'm not. I'm primarily going to be talking about the context of Plasma and the relationship between public and private chains. But in order to do that, I sort of need to give a high-level overview, so that'll maybe consume like 7 minutes of it anyway. So Plasma is a way to do blockchain scalability. It's not the only strategy. Ethereum's doing a lot of things like sharding, and this runs on top of it as a layer 2. Plasma was released like 2 months ago as a paper. Currently starting development soon. If you guys are interested, definitely reach out to me. Yeah, so it was released by me and Vitalik 2 months ago. So what is it? It's a set of nested blockchains, so blockchains and blockchains, and that allows you to do scalability. And basically you have this blockchain like submitting small pieces of information about the state of this child blockchain into the Ethereum mainnet. And this is not a proof of existence, right? It's not just submitting timestamps and timestamps only. It's enforceable. So if you submit bad data and other people can prove it, you get penalized, and that's called a fraud proof. And what it is a set of smart contracts. There is no token sale. You can put tokens on top of this, and it helps with the security, but it's not inherently some kind of token mechanism is not required. Literally, it's pieces of software. You modify it to do whatever you want, and then you submit the code onto Ethereum, and then now you can launch a child blockchain. And that gives you an incredible scalability. And in order to do computation, because you're dealing with different sets of blockchains, we have a lot of experience with this over the past 20 years using things like MapReduce, and there's a lot of defined algorithms to be able to do this, to be able to spread out the work across the blockchains and then take the results and be able to compute on it. And like I said earlier, this is compatible with other on-chain scaling solutions, so capacity increases on the base layer, increases the security and performance here. So the design goals of this is that you can do all worldwide computation on Ethereum. And the goal is trust minimization. So the activity in this child blockchain should be as untrusted as possible. So if the participants all actively try to steal your money, you should be able to find ways to get out of it. And the paper defines the specific mechanisms and security assumptions and properties. And this can give you payment and ledger scalability. We're talking about the potential to have like billions and trillions of records, not just transactions, but records as well. And the goal is to be able to do billions of state updates per second on this network, which is publicly accountable on the public chains. So how does this work? Essentially, you upload the smart contract onto Ethereum, the Ethereum public blockchain, and this allows you to launch your own specific applications with your specific rules. So for example, you can launch some social networks, some micropayment systems, some decentralized exchange, or more interestingly, in the context of this talk, a private blockchain. So you can upload public code onto the public network and have a private blockchain which is enforceable on a public network and creates incredible scale as well. And the way this is done is by periodically committing to the root chain. Oh, they got the focus off a little bit, whatever. So if you can sort of see right here, it's sort of like Alice has some transaction or some state on this Plasma blockchain going on, and then periodically hashes of this block get committed on the public chain. If this state is incorrect, this gets canceled and rolled back if anyone can publish a proof that the information in block number 3 is invalid and violates consensus rules. So this is about the nature of enforceability. Enforceability is very, very, very important and is the core of blockchain. If you have a blockchain that's not enforceable, it's just role-playing. The cool thing is this allows you to watch only the chains that affect you. So if you have money over there in the third tree depth, they're doing computation, you only need to watch its parents. All the other activity may not be relevant. Sometimes you need to watch everything, but not necessarily. And this allows you to do computation, so you map out the computation, and then you reduce it back down to get the results. And MapReduce, invented by Google, basically one of the core, tricks of distributed computing. So why is this interesting? We're talking about a system of blockchains and blockchains, and if you view blockchains not as purely a payment mechanism, but a court system, right? We're talking about a system of courts in order to scale, right? The Supreme Court doesn't look at every single contract that goes on. It's only in the event of dispute that you go to court, right? So you don't go to court every time you write a legal contract with your employer or whatever it is. So it's only if there's an event of dispute, you go to the blockchain. And when you go to the blockchain, your local blockchain handles the traffic, handles the adjudication, and it's only if it's computed incorrectly that you can attest the states to its parent. And ultimately, the public chain is sort of the supreme court of this global system. And that brings you incredible scale because it's only if the lower district courts computed incorrectly that you ultimately have public global enforcement. And this allows you to do high-volume, low-cost decentralized applications and could be an interesting path forward for computational scaling and compatible with sharding. The goal here is not just billions of transactions, but billions of users and potentially trillions of ledger entries, right? Like if we're dealing with machine-to-machine payments and things like that, where each device has to have its own ledger entry to represent itself and take action, you may be requiring a lot of transactions, a lot of ledger entries, and a lot of state modifications. Additionally, earlier I was giving examples of this child blockchain created by someone. You could have a distributed system where you have tokens issued so that there is this token model for these child blockchains, where these child blockchains issue tokens to give it economic security against halting and incentives against halting. Use cases for this: ledger scalability, decentralized messaging, file caching, social networks, and private blockchains. So I'm going to spend the rest of my time talking about this topic. There's a defining narrative around token models today, private versus public, and a lot of these dialectics, I think, will probably be resolved conceptually, maybe not in terms of code, but conceptually probably within the next 2 years. And saying that you want a private chain at its root, I'm editorializing slightly here, but this is really what I believe, right? If you have a private chain at its root, you're ultimately trusting that private party or set of private parties to represent what is the global state. It's sort of like if you only had an intranet and you said, oh, intranets are what matters. And it's like, no, the internet is what matters. It's the connectivity. It's the boundary between organizations, right? It's the boundary. The theory of the firm is the notion about internal versus external. And when you deal with these topics, fundamentally, it's the aspect of the external interrelationships between parties, which is what's interesting. You can treat the public Ethereum chain as a DMZ for private chains, right? A sort of like this demarcation zone, right? A demilitarization zone, where these multiple parties, these multiple blockchains can interoperate and intercommunicate. And the goal is that the enforceability of this public network allows private parties and private blockchains to be able to interact in a trustworthy manner, right? Imagine if a bank opened this private blockchain and I'm willing to deposit funds there or do transactions there, state transitions. What does that really mean for the trust that I'm ascribing to this institution? Right? On a competitive basis, if this institution says, I am committing my activity onto the public chain, and if I violate these rules, I will get penalized on this public network, and I can't do anything about it. The assurance there is incredible, right? We're talking about a system where you can sort of have your cake and eat it too, where you can determine the rules. You can determine, who's allowed to transact, who's allowed to conduct transactions, what type of transactions you're doing and the context for it, and the information availability of it on a private network. But in the event of disagreement, you can go to the global public network and enforce it. And that way, the trust in you, as let's say if you're a bank operating the system, that allows you to be able to tell your customers, hey, use my platform. You don't need to trust me, because if I try to screw you over, I'll get heavily penalized on a public network that I don't control, right? You can control the operation of this network, but you are binding yourself to following the rules. And this is a new way of thinking about the interoperability then the context between private and public systems. And this is sort of, I believe, going to be an emerging narrative that's going to be the defining context next year for a lot of enterprise. But of course, this stuff does take time to develop and understand the security properties and the scalability properties. But a lot of this is sort of where we're headed, and it's sort of an introduction and starting the conversation within the context of enterprise chains. Thank you so much. Yeah.